without further ado, talk about dynamics. Okay, so the first thing I'm going to talk about are translation surfaces. Okay, so what is a translation surface? A translation surface is surface X together with a non-zero holomorphic one form. We're going to call omega. So this non-zero holomorphic one form can also be called an abelian differential. Okay. How many of you do not know what a holomorphic one form is? Couple? Okay. No shame. That's fine. So, how do I think about my holomorphic one form? I want to think of it as omega tells me how to integrate curves. So it's really an element in cohomology, is how I want to think about it. So we're going to actually understand how to see these very concretely through examples throughout the talk. So, I want to give you an example, but to give you an example, I'm going to give you an equivalent definition, which allows me to write the examples really nicely. So it's a collection of polygons in the plane with sides identified by translations. Up to some equivalence.
This is polygons and
C.
Also, one hint, maybe do not write to the very bottom of that blackboard.
Yeah, I see. Uh-huh.
I mean, it's okay now. Just
yeah, we won't go there. In the future, we're gonna say what. Okay. So the first example, I'm going to give you the example of the torus, and the one form is DC. So I want to take the torus, I want to view it as a polygon sitting in the plane. I want to glue opposite sides. Hopefully most people have seen this. You can also see this as the complex plane, mod Z plus IZ. We've already seen this in some previous talks. So I want to take the torus, and what I'm incorporating, I said I want to mark a holomorphic one form. So for those of you who are less comfortable, what is a holomorphic one form? Well, if I take a closed curve gamma, my holomorphic one form says I want to integrate my closed curve gamma with respect to my one form, and it just gives me my horizontal and vertical displacement. Okay. So this is one example. So already we had people talking about elliptic curves, the space of elliptic curves. This is something that's going to be coming up. But then what happened, for example, in Anna's talk is we went from the space of elliptic curves to the space of abelian varieties. And instead of going to the space of abelian varieties, I want to go really keeping track of a one form. I want to go to higher genus Riemann surfaces. So this is going to lead me to my second running example. L shape. Okay, so now I have an L shape. This is a genus 2 surface, which I'm going to just tell you. You can do an Euler characteristic argument. This is like the only place I know where like regularly in the field we'll just draw pictures and be like, okay, time to compute the Euler characteristic. So we do this a lot. It's very fun. Okay, so what I did is I just drew a polygon in the plane. My sides are identified by translation. And something funky is going to happen here. So if I take, for example, my vertices, if I take the top of one It's glued to the top of 1, to the bottom of 4, to the left of 2, to the right of 3, to the top of 4, to the left of 3, to the bottom of 1, up to the top of 2. So I actually have all of these red vertice points mapped to a single point. So if I look at this single point, this says angle pi around it. So you can add up the angles around here, and the angle is 6 pi. So now what's going to happen to my one form? So I want to have a local chart, because this is a Riemann surface, so I can have a local chart at points. The local chart inside my surface is just going to be the identity, but then the local chart at the vertex, well, what am I going to do? I want to have a map from the complex plane to a neighborhood, let's call this map P, and I want this map to go to this neighborhood with angle 6 pi. So in particular, I need to take Z maps to Z cubed. This is going to take my 2 pi angle, wrap it around to give me 6 pi angle. So now, when I take the derivative of Z cubed, I get 3Z squared dz. So in particular, when this is my translation surface L omega, I want omega is going to be dz away from my vertex. And it's going to be d squared dz at the vertex. So this is what it locally looks like. And so I said I want to take a non-zero holomorphic one form. Well, it's always going to have 2g minus 2 zeros with multiplicity. So my one form omega is non-zero, but I do have some zeros showing up. And these zeros are marked points that I want to keep track of as I move throughout the moduli space. Okay, any questions on the definitions of a translation surface? Okay.
Only one question on the example of this L shape. You have 4 edges marked with these 3 markings to be identified. Are these all 4 edges identified as one, or are there 2 pairs and I'm missing like 3 depicted?
This is
no,
like this one?
No, the one next to it. Yes, that one.
This
and
is
the 3 on the
3.
and these other 2 are 4s.
These are V's or 4s
Okay.
or 5s, 4s.
Thanks.
Okay, so now I want to look at the moduli space of translation surfaces. So when I'm looking at the moduli space of translation surfaces, this is going to be omega mg, where omega is the Hodge bundle. This omega mg is the Hodge bundle. So for those of you who are familiar with working with the Hodge bundle, you can see it as, okay, the total space of the vector bundle over the universal curve. So there was a lot of discussion about working with universal curve. If you're familiar with it, there's a lot of stuff that you can know about this. If you're not familiar with it, it's just kind of a moduli space. And I want to just, take the space of holomorphic one forms over PhD surfaces. That's all we're doing. Okay, so I said I do dynamics. So the first thing we're going to do is say, what are the dynamics? And then we're going to talk about why dynamicists care about combinatorial algebraic geometry. Okay, so the dynamics is I have an action of SL2R on the polygons in C via an R linear. Okay, so here I want to take the vector 1, 1, 0, 1, and I want to act on the unit square I plus 1. And what does this do? This gives me 0, 1 plus I. 1, 2 plus I. Gives me a different translation surface. And I can cut and paste. So this is, I said that my polygons are identified up to equivalence. This is going to be a cut and paste. And I can cut and paste back to the original square torus, where this side is this side, and then this side is here. Okay, so this board situation is awkward. Okay. So I said I want to understand the Hodge bundle. Well, if I want to take the Hodge bundle of M1, what I'm doing is I'm taking SL2R, and we just showed that we have, okay, this matrix gives me a stabilizer, and you can actually show as an exercise, the full stabilizer group of this action is going to be SL2C. So for context for what happened before, this is the unit tangent bundle, of the upper half plane mod SL2C. So what we're really doing is we're taking elliptic curves, we're taking the moduli space of elliptic curves, with a notion of north or up. We have a fixed orientation of our curves. And so this is going to be the same case in higher genus. You're going to take the moduli space of genus G curves, and I'm adding this information, which tells me what is my notion of up. Let's see. Okay. So when our genus is bigger than or equal to 2, we always have x omega with omega has 2g minus 2 zeros with multiplicity. And with these 2g minus 2 zeros, the SL2R action preserves these zeros. With the SL2R action preserves these zeros. So we have a stratification. I said we want to talk about the moduli space, and it actually doesn't really make sense to talk about the moduli space all at once. I need to talk about the moduli space, omega mg, and then I want to add, what did I use, alpha. So omega mg of alpha is then going to be the stratification for the multi-index is alpha 1 through alpha n, which is a partition of 2g minus 2. So if we go back to this example, so in the case of the torus, well, I have to have one marked point in order to actually work with this. So I am going to allow having zeros. So this was in facts. I missed a fact. Okay. I did miss a fact. Okay, so we have the stratification. Each has, at most, 3 connected components. And each connected component, and we'll just work with one. We'll call one of them H of alpha. So these connected components, they're classified according to their spin invariance. So there's going to be one connected component, or we can have hyperelliptic components, or we can have positive and negative spin, which is something that comes up here. So for that, that's not so important for what we're going to do. So then for the case of the torus, we have we're in H of 0. And for the case of the L, we're an H of 2 because we have one singularity, but our singularity, our 0 is of order 2. Because we have z squared d squared. Okay. Any questions? Okay. So, there's a theorem to Maser, Smiley, all early 90s. So Maser and Beach constructed this in 89. Smiley and Maser constructed the rest of it in 91. Said, okay, there exists a unique SL2R invariant measure on H of alpha. So they construct this probability measure, SL2R invariant measure, which is a probability measure. Okay, so what do I need in order to do dynamics? Well, I want to work on a probability space so I can say what happens on average. I can really say something measure theoretical. Yeah?
Is there any information about these partitions? Like, why are we so defined by partitions of 2D and 3D?
Yeah. So, okay. So, what I am going to say, black box theorem is every holomorphic one form has 2G minus 2 zeros with multiplicity. Because you can't put on higher genus surfaces, you can't put a non-zero holomorphic. There's no non-zero ones. Okay. So if we black box that fact, now I want to say, okay, what happens? How do my surfaces kind of how do I understand them living together? And so for one example, I'm going to take a torus and I'm going to take another torus. Okay, and I want to take these two tori and I'm going to glue them along a slit. So I'm going to take this slit, assume this is identical on each side. This is side A, glues to side A, side B, glues to side B. So now, if I want to understand what happens, okay, so I end up with 2 zeros of order 1. And what can happen is these zeros, if I they can collapse. And so what actually happens is this H of 2, this really lives in the boundary of this space H of 1, 1. So we want to stratify it because when I'm working with SL2R, when I'm working on these actions, I get this natural stratification. Then when I start to take closures, I need to understand how they relate to each other.
So the alphas are then the multiplicity.
Yes, exactly. More questions? Yeah.
Remind me of this H notation, this H of 1, 1.
Yeah. So this alpha is 1, 1 here. So this is my partitions of the zeros. And the H is this technical fact that I want to take the moduli space. But the moduli space gets cut up into connected components. And as soon as I'm in a connected component and I'm acting by SL2R, I can never leave that connected component. So I have to further restrict to a connected component H. Yeah. Okay. Okay, so I'm already hinting at we care about closures, and closures are going to become very important. But before we get there, I said that my measure I'm going to call this measure mu. I have this SL2R invariant probability measure. So what happens on the torus? Well, on the torus, we said there was I think in Anna's talk, we talked about if we take the unit tangent bundle of SL2R on SL2Z, what we're doing is we're taking the fundamental domain for the modular curve. And the measure mu is exactly the hyperbolic measure. So dx dy over y squared in the upper half plane times d theta over 2 pi. So we're going to get a circle because I have to take the unit tangent bundle and I just integrate over the circle with the thing. So mu is going to be the hyperbolic measure with the circle measure, and then I just have to normalize for this to be a probability measure. And this is finite volume because we have a hyperbolic triangle. Hyperbolic triangles have finite volume. Okay, so this is what happens on the case of the torus. But in general, we don't actually have this nice global definition for this measure. We have to talk about actually locally how we construct it. We can only talk about mu locally. And the way we can talk about mu locally is mu is locally the Lebesgue on C to the 2G minus the length of alpha plus 1. Plus the length of alpha minus 1. Okay. So how do I find this? I'm going to take period coordinates. So I'm going to take gamma I from I equals 1 to 2G plus the length of alpha minus 1 is going to be a basis of the relative homology. So basis of the relative homology, I have my standard 2G basis elements, plus I have to add up to the length of alpha minus 1. These are marked points, and I have a relative homology for my marked points in MGN. So you can really think about this living in MGN. And these are period coordinates. Where I did not do good board position. Okay, I'll do this here. Okay, so the measure mu is locally cut out by period coordinates, which means I'm going to go from I want to take the integral over my basis of homology of my one form of I equals 1 to 2G plus the length of alpha minus 1. This lives in the complex number C to the 2G plus length of alpha minus 1. Okay, so what does this mean? If I go to this example, I'm just going to keep decorating this example. Here, in this case, so we're going to remove some of these decorations so that we can keep track of what's going on. So in this case where I'm taking the L shape, well, I want to take a basis of relative homology, genus 2, and I have one marked point. So I should have 4 vectors which actually cut out my surface in these local coordinates. And these 4 vectors are V1, V2, V3, and V4. So I can really just take, if I want to understand my measure, I can actually just take local neighborhoods around these vectors. Those give me little deformations of my L shape, and the Lebesgue measure of that is actually the Lebesgue measure of this neighborhood. The miracle is that these all glue together to be a finite measure. Okay, so does anyone have questions on the measure? What we're doing? Now I'm talking to algebraic geometers, so I know I'm doing measures. I know I'm doing SL2R orbits. We're getting there, I promise. Okay.
Yeah, maybe
Yeah.
I didn't get the last example with the vectors. Like, yeah.
Yeah, so these vectors, like if I take an L shape, these vectors v1, v2, v3, and v4. So I have 4 vectors, and they define my L shape. Because then they each just have their opposite gluing. And then what I can do is, let's say I want to deform v2 down a little bit, but I'm literally just like taking my L shape and I'm just taking this part and I'm just pushing it down a little bit. So I'm allowed to move within this moduli space by actually just moving in the complex plane with these vectors.
Okay.
Yeah. Okay. So that was everything we needed for translation services, and now we get to really exciting stuff. So I want to talk about orbit closures and classification. And this is exactly where algebraic geometry is going to be coming in. So okay, so what do? I'm a dynamicist. I want to understand orbits under group actions, and I want to say what happens for typical points with respect to invariant measure. That's what dynamicists do. Okay, so I want to say, what do we know about orbit closures? I want to take SL2R tied to X omega, and I want to take an orbit closure. So now I'm going to skip a lot of history, and we're going to go straight to winning big prizes. So we're going to talk about Eskin, Mirzakhani, Mohammadi, 15, and then there's a further paper in 2018 by Eskin and Mirzakhani. Mirzakhani won the Fields Medal for this, Eskin won the breakthrough prize for this. So I'm going to give this in like 2 sentences. There's a lot of background going on here. So what do we know? If we take SL2R, we apply it to X omega. It's cut out by linear equations. And by linear, I mean actually no constant part. We don't allow constant parts because with SL2R, we always translate those away. So it's always cut out by linear equations with real coefficients. In period coordinates. So I went through all this effort of defining period coordinates. I said there's this measure I care about, which is defined in terms of these local period coordinates. And when I'm studying this measure in terms of local period coordinates, I'm actually able to cut out linear equations. So we took something that was very analytic, very much living in the analysis world and dynamics world, and all of a sudden we have algebra coming in. So there's a further result by Philippe. And he says these orbit closures are also called affine invariant submanifolds. Are algebraic varieties. Okay, so we don't just have local coordinates, we actually have algebraic varieties. Now we're really in business. We're talking about algebra. And so for those of you who aren't as familiar with these things, I just want to give a very concrete example of the fact that there's a lot of abstract math going on here, but we can just do concrete computations and actually see what's going on. So what I'm going to do is I'm going to take a torus. This lives in h of 0, as we said, and I want to lift it to a threefold cover. So my torus, I want to have this, let's say this is the vector A, this is the vector B. And now I'm going to lift to a threefold cover. So I have this one, this one, this one, and hopefully this looks very familiar. Now we have an L-shaped translation surface. I'm actually not going to put those in so this picture doesn't get, but we have the opposite sides are identified. And now I want to take again these sides, V1, V2, V3, V4. Okay, so now I said I have these vectors defining my local period coordinates. And my equation is V1 is equal to V2, V3 is equal to V4 is equal to the vector V. And these are my linear equations. Okay.
So that's describing the orbit of this L shape.
This is saying if I want to take, so I have this L shape, I'm in H of 2. This is like a, this is like the orbit closure locally for the threefold torus covers. I'm taking these threefold torus covers, and I want to say, how does this look locally? And these are locally cut out by that. More questions? Okay. So what I'm going to do is I'm going to tell you a quick spiel about, okay, this is, we need to understand orbit closures. And I'm going to tell you that in order to understand these orbit closures, we know that they're locally cut out by these linear coordinates. We know they're algebraic varieties, but we still cannot classify them. There's still a lot of combinatorics going on, and I want to give you some idea of why these combinatorics are still going on. And the way these combinatorics show up is when we're degenerating sources, when we have sources of non-compactness, and we want to go to the boundary.
Is there any chance we can say something about the algebraic equations defining the varieties?
There are some specific cases.
Okay.
So that is something that, okay, so we can say, but in terms of more specific examples, so there's something called like the Goethe focus where people can understand this. People can understand these with hyperelliptic loci, with rim varieties. So when you have more structure, yes, in general, no.
Okay.
And there are some results that you can say what happens, in very high rank situations. So that's where things really break down into cases, and we don't have a universal answer. Okay, so so in order to understand these order closures, so what we want to do is we want to understand non-compactness. So first, how are we not compact? And second, how to compactify. Okay, So there were quite a few talks where people said, let's go from our nodal curves, then we can get the dual graphs from the dilemma for compactification. And we want to do the same idea, but we're going to end up with some decorations. So in the first example, I want to take a torus. So I want to take a torus. I want to have side length 1, and then length 1 over epsilon. And I'm going to take epsilon going to 0. So if I take epsilon going to 0, this is really a torus. I locally have x epsilon, and I really have dz as my differential here. But now, as I go off to infinity, I'm going to end up with this like half infinite cylinder. So now we have this half infinite cylinder, and for convenience, so we can follow what's going on, I'm going to add a marked point. So here is going to be my marked point, so I can really keep track of, where am I going off to infinity. So what's happening in the Deligne-Mumford compactification is I'm taking this point, and then I'm developing into this nodal surface where I go off to infinity. So underneath, this is what's happening. So we have this is our Riemann surface. We're degenerating to this nodal surface. But I want to talk about what happens at this node with my one form. And the way that I can understand what happens with this node at my one form is, well, just like in the case of the L, we want to have a local chart, psi, which goes from the disk. Pretend that's a disk. So I want to have a map psi, which goes from the disk into my half infinite cylinder. Well, what's the map which goes from the disk to a half infinite cylinder? If I puncture it, it's log of z. So I take z, maps to log of z, and this is my local chart. And now I want to take dz as my one form. So if I take dz, I'm going to get a 1 over, I want to clip this with d of log of z, which is giving me a 1 over z dz. So what we just did is we said, okay, I want to understand the space of holomorphic differentials, which locally look like a holomorphic function times dz. And I wanted to generate to the boundary. In order to generate to the boundary, I'm going to have poles showing up. So my nodes are going to correspond to poles of my function. So now we have to work in the space of meromorphic differentials. You get nothing else out of this talk. That's the example. That's just like, I think one thing that really frustrated me when I was first starting to learn this, because I come from a dynamics perspective, and I was trying to learn the Riemann compactification and understand what it means. It was very hard for me. Like I was like, people were like, okay, yes, you can draw these dual graphs, but then going explicitly back and forth is very hard. And one thing I love about this is I can now explicitly see it, and I can just do the computations with complex analysis, and I'm like, I got it. So it's very helpful. Okay. How are we doing on time? Great. Okay.
Sorry?
Yeah.
So can you see this as a log geometric term with a holomorphic one form? Log with a holomorphic one form?
I'm not so sure, because it really only comes from the local charts. And in terms of the one form, we only see the differentials. Like I could just say I only care about meromorphic differentials, and you would never see the logarithms.
But in this setting of logarithmic geometry, I don't know if there is a
There is.
There is?
Yeah.
Care to elaborate? Shortly.
But I don't know. I mean, there is a framework to study these sort of limits from a block geometric perspective.
Okay.
Which is, I think, on the archive now by the other Martin in this department and many others.
Okay. Okay. So
It's maybe the only thing I can say.
aren't in this department and lots of others. Apparently there is this log geometry.
Yeah.
This is where, okay, he becomes here because what the idea was that's been happening in the field over time is you say, okay, I want to define the compactification. So I really want to have a compactification, but the compactification has to still respect all the information about my holomorphic potentials. And so there's been a series of compactifications since 2015. Which go all the way back to what's called the WYSIWYG, is what you see is what you get compactification, which basically forgets what happens when we compactify. So what I'm going to tell you about is the most recent, which is called the multi-scale compactification.
That one is also secretly logarithmic.
Also secretly logarithmic. Amazing. I don't think about logarithmic geometry. You can say. Okay, so this is the BCGGM, which was most recently updated in December of 2024. Still not published, but it was originally posted in 22. So this is an ongoing updating process. This is the nicest multi-scale compactification, because what it does is it's going to give us a compactification, which gives us actually a projected algebraic right. So instead of giving you all the details, because this is a massive paper, it takes a long time to understand, I just want to give you one example to give you an idea of we're taking holomorphic differentials, we're degenerating over the space of the Hodge bundle. So we want to understand, this lives over the moduli space. So we're working with the Billing-Mumford compactification with decorations. And I want to give you an intuition of why might there be multiple scales. Instead of a definition, we're just going to do definition by example. And so what I'm going to do is I'm going to take a torus, and then I'm going to take a smaller torus, and then I'm going to take a smaller torus. Okay. So I have my tori. So this is the genus 3 surface. I want to glue A1, B1 is going to get glued here. And then my other one, I'm going to say be here. A2, B2 is going to get glued here. B2, A2. Okay, so I'm taking my tori and gluing them along slits. And now what I want to do is I want to degenerate in epsilon. So this is going to be my surface x epsilon, where this surface has size 1, this surface has size epsilon, and this surface has size epsilon squared. So I'm going to multiply these surfaces by epsilon, epsilon squared, and 1. And I want to say what happens as epsilon goes to 0. Well, in the dual graph, what's happening is I'm going to get 3 connected components. But what I want to do is I want to keep track of these connected components in terms of when they shrunk. So this epsilon squared term is corresponding to something of level -2. And then this term here, where I'm degenerating by epsilon, is going to have a level 1. And then my one that, I'm not degenerating, I just have attached points to this middle surface is going to have level 0. So what I'm doing in the multi-scale compactification is I'm decorating my Billing-Mumford compactification with levels. I need to keep track of the order of the poles. So this is something I'm hiding here, but this, we got a pole of order 1, we have 1 over z, and generally you have to keep track of the order of your poles at the nodes. In particular, we need the order of the poles at the nodes to work so that we can actually glue things together. And the zeros are kept track of via the half edges, so just like in MGN. But with the order of the 0, keep order of the 0. In particular, the reason I say Martin Muller et al. Is if you Google Martin Muller or St. Bruszewski and you try to see what's going on, intersection theory, computing cohomology, this is what they can now do with this compactification. Questions, comments, protests?
Homology of your
Like, you can compute the cohomology of the moduli space and understanding that cohomology works. Yeah.
Very few, right?
No, this is like, what do you mean all of them? So there's very few. There's very little that they can say about it.
Okay,
is what
yeah,
I'm gonna say right now.
Okay. Yes.
There's
I
some
agree.
very specific examples where they can do some things. But there's not, it's hard. There's a lot of combinatorics to keep track of. Yeah, okay.
Why do you get 1 and -2 for the levels?
So the level, that should be a -1. Yeah. So the levels is you always want 0 to be your top one, and then it's just always the integers below. Yeah. Okay, so in the last couple of minutes, what do I want to say? Okay, so I said we're going to go from dynamics. Dynamics, we care about orbit closures. In order to understand orbit closures and what's really going on, we have to understand the domain boundary compactification with decorations in order to understand what's happening on these space of holomorphic differentials. Okay, so now in the last few minutes, I want to say, okay, this is nice. This doesn't really tell you why this is important for obtaining dynamical information. So I want to go back and say, here's the compactification. Now I'm going to hide all of the compactification details because this takes a long time to understand. And I'm going to just say the compactification is used to prove information that we need in order to do dynamical statements. So we're going to go back to dynamics. Okay, so back to dynamics. I said I want to understand. Okay, so here's what I'm going to do. I want to define a saddle connection is a geodesic starting and ending a 0 of omega. These are very simple. For example, if this is the L shape, I can take the geodesic here, and this is the saddle connection. Okay, and as I already mentioned, I can take lambda is going to be the set of integrals of gamma against omega such that gamma is a saddle connection. And this is a subset of the complex plane, which is discrete. So as our canonical example, in the case of the torus, the lambda of the square torus is equal to SL2Z applied to 1, 0, which is equal to the set of all A, B in Z2, such that the GCD of A and B is 1. already there's going to be a lot of somehow connections to Anna's where we're really saying, okay, I want to understand primitive vectors in the lattice and how do I work with these? In general, they don't have to live inside of the lattice. In general, they don't live inside of the lattice, actually. Okay, so what can I do in the case of primitive tori? I can say how many primitive points are there in the ball of radius R?
Sorry, how are you getting that into C?
Oh, sorry, this isn't C. C is R2. A plus IB. Yeah,
Okay.
yeah. Yeah. Is it, I don't want to think so. Okay. So, the question is, can we understand, for example, how many points are there in the ball of radius R as R goes to infinity? And in fact, if we want to understand what happens as R goes to infinity, well, we're going to have quadratic growth. And this is going to be some constant called the Segal-Beach constant. So in the case of the torus, C is equal to 6 over pi squared, which is 1 over zeta of 2. And this captures the fact that primitive lattice vectors have density 1 over zeta of 2 in the integer lattice. So now this is great. You get the Segal-Beach transform. In the case of the torus, this is nice. In general, they again use combinatorial algebraic geometry to compute these. These are computing natural volumes on these spaces. So in order to compute these constants, you really need to use that. But what I want to advertise is what is hard about these counting problems. So I have quite a few results counting. So for example, when I want to count pairs. So for example, there's a result with Freya Mazer 23, I think, maybe 24, I don't know. Where we say, okay, let's say I want to count the set of all vectors VW in these saddle connections where V wedge W is less than or equal to A. So I want to count points where I want to take vectors where their area, the matrix, the area of the parallelepiped that they make has area less than A. We say, okay, well, for mu almost every surface, the limit as R goes to infinity of this NA of omega R over R squared is equal to some constant CA. And one of the things we're trying to do is we're trying to understand this constant CA and how we can do this. This is now in the process of being generalized. Sorry, this is for a special case. And now it's in the process of being generalized to all orbit closures with Bonafu. Probably 25 plus, who knows? What we're doing is we're generalizing it. We can get the same result. And the idea, we have to use regularity of the measure. So what I want to do is I want to say if I have short saddle connections, so let's let's say S1 through Sn with the length of Si less than epsilon I, then the result by Dozier, also in 23, says that the measure of the set of where we're having short saddle connections is on the order of epsilon I squared, epsilon 1 squared through epsilon n squared. So what this does is this allows us to say, so I want to count the number of, I want to count vectors. What happens as I go off to infinity, for example, as I'm doing this, if I want to count the number of points in the ball radius 1, I'm going to get a lot as epsilon goes to 0. So I have to control what happens at the boundary when I have short saddle connections. To control the boundary, what we do is we say, we don't need to control the boundary, we just need a really small measure, and then it's not a problem. So this is the key point, is regularity, and the proof of this result uses the multi-scale compactification. That's all.